Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to talk on the module MEMS based Enose under the paper Semiconductor Materials and Devices. So students, let us see what we are going to learn in this module. First, we will discuss what is Enose. Second, MEMS, microelectronic mechanical structures. Third, fabrication of Enose. Next, we will also discuss about dicing and packaging. Lastly, working and applications of MEMS Enose will be discussed. So students, let us start with a basic introduction about the module. With advancement in technology, number of pollutant gases has been increased significantly. As we all are aware of gases from factories and vehicles, which contains very harmful gases such as CO, CO2, NO2, SO2, methane, etc., which leads to various health problems to the mankind. In view of this continuous monitoring of different gases at various places, especially at resident areas, is essential. So, in order to monitor the multiple harmful gases on a single platform, Enose devices can be fabricated using MEMS, microelectronic mechanical structure technique. As the name suggests, Enose is some kind of electronic nose sensing the concentrations of various gases similar to the functioning of our nose, which keeps on sensing the different gases and keeps on identifying the type of a gas. Metal oxide based gas sensors are the most popular sensors when talked in terms of the ease of miniaturization and mass production. So, metal oxide gas sensors, which consist of a microheater, interdigitated electrodes, and a metal oxide film. MEMS technique is a technique in which micron-size mechanical structures can be fabricated using the photolithography and micro-machining technique. As we have already learned about photolithography and micro-machining in our previous modules, so here we will learn to make MEMS-based Enose using photolithography and micro-machining. So students, let us discuss what is Enose. Enose is an array of sensors with different sensing layers deposited over it. So on interaction with a gas, each sensor will give different response, helping in identifying the type of gas. So different kinds of sensors can be used as gas sensor, such as surface acoustic wave based optical conductometric, etc. The two main components of an Enose are the sensing systems and the pattern recognition system. The sensing system has an array of different sensing elements, for example, gas sensors, where each element is designed for a particular odor, gas, thereby responding by various magnitudes to individual odor or gas or to a combination. Each odor vapor presented to the sensor array produces a signature or unique pattern characteristic, fingerprint or smell print of the vapor. So students, by presenting different chemicals to the sensor array, a database of signatures is built up, which is used to train the pattern recognition system. The training process is to configure the recognition system in order to produce unique classification of each odor so that unknown odor could subsequently be classified and identified. Now, the most commonly used Enose sensing technology is based on metal oxides. These sensors are generally operated at high temperatures and therefore have high power consumption, around 800 milliwatt for Taguchi ceramic sensor. Therefore, extensive research is continuing towards the fabrication of smaller and more energy efficient systems such as thin film metal oxide sensors or microfabricated silicon planar sensors. In metal oxide gas sensors, microheaters are used as micro hot plate, which provides constant and uniform temperature to the gas sensing film. Sensitivity, response, and recovery time of the gas sensor depends on the performance of microheater. Now, various parameters such as microheater geometry, size, and material are considered to make low power and thermally stable microheater. Students, however, one needs to optimize the miniaturization along with sensitivity, as small area for sensing may lead to saturation at higher concentrations. Different geometries, namely S-type, meandered shape, fan type, double spiral, etc., have been explored for microheater element considering temperature uniformity and power consumption. Various materials such as platinum, polysilicon, nichrome, tungsten, gold, etc. have been explored for microheater application. However, platinum is a clear winner generally due to its stability at high temperature values and chemical stability. Physical verification of the temperature and its uniformity is carried out by infrared imaging. Power consumption of the microheater can also be optimized using the pulse mode of operation. Now, let us discuss the example of metal oxide based conductometric Enose. Schematic is shown in this figure, and it can be seen from the figure that there is an array of sensor with different sensing layer. Each sensing layer is represented by different color. It may also be noted from the figure that each sensor contains 4 contact pads, 2 corresponding to heater and 2 for electrodes. Heater is incorporated with each sensor in order to provide necessary operating temperature for sensor functioning. MEMS, or we can say microelectronic mechanical structures. Microelectronic mechanical structures are the electronic circuits which are fabricated on a very thin membrane. So, being fabricated on membranes, MEMS devices offers various advantages over conventional devices such as small size, high sensitivity, and low power consumption. Schematic for the MEMS devices is shown in this figure. Now here, silicon bulk micro machining is used in order to fabricate the MEMS devices. So for the bulk micro machining of silicon wet as well as dry etching technique can be followed. Each have their advantage and disadvantage. As can be seen from this figure, a cavity is fabricated on the black side of the device using bulk micro machining, and interdigital electrodes have been patterned on the front side on silicon dioxide membrane in order to obtain a MEMS device. Fabrication of Enose. Now there are various steps which are used to fabricate the Enose, and these steps will be discussed sequentially. First is cleaning. First step towards the fabrication of microelectronic devices is wafer cleaning. So the silicon needs to be cleaned thoroughly following the standard process of cleaning, including RCA1, RCA2, and Piranha Cleaning. The sequence of cleaning the silicon wafers was first introduced by MS Werner Kern, an employee of Radio Corporation of America (RCA) in 1965, and is therefore often referred as RCA process. This chemical sequence does not chemically react and attack the silicon. In fact, it removes the contamination that resides on the wafer surface. So cleaning of silicon wafer is carried out using the sequential process, which will be discussed in the later slides. Piranha Cleaning. Now, students, this is the first step of the cleaning of silicon wafers, where they are first cleaned in Piranha solution, which is a mixture of sulfuric acid and hydrogen peroxide in 1:1 ratio. Organic and inorganic contaminations are removed from the wafer. So cleaning is done for 2 to 10 minutes is recommended, and subsequently wafers are rinsed in deionized water and dried with the jet of dry nitrogen gas. Now, second step is RCA cleaning. Ionic and metal contamination present on the surface of silicon wafer is removed using RCA solution. Now here, RCA solution consists of a mixture of DI water, that is HCl, H2O5 in 5:3:3 ratio, and the solution is heated at 70 degrees Celsius. Now here the cleaning process is carried out for 20 minutes. Finally, the wafers are rinsed in DI water and dried with a jet of dry nitrogen gas. Next is the oxide removal. To remove the native oxide from the silicon surface, wafers are dipped in a solution of HF-DI water, that is in the ratio of 1:20 for 5 to 10 seconds. Finally, wafers are rinsed in DI water and dried with a jet of dry nitrogen gas. Now, HF is extremely dangerous and must be handled with great care. Students, let us now discuss about thermal oxidation. A sacrificial layer of SiO2 is needed on the surface of silicon wafer for the selective area etching after opening of the window. The SiO2 can be grown on the surface using thermal oxidation. Therefore, oxidation of silicon wafer is the most important process. So, three-zone thermal oxidation process is used to grow a thick film of SiO2 over the silicon wafer. So, thickness of SiO2 thin film strongly depends on the oxidation time and temperature. So, thermal oxidation is carried out at 1100 degrees Celsius plus minus 10 degrees Celsius in 100% oxygen ambient. The wet oxidation of silicon was performed for 10 hours by passing water vapors with oxygen gas. Dry oxidation is carried out initially for 30 minutes, followed by 10 hours wet oxidation, and again dry oxidation for 30 minutes. The presence of residual water molecules from the wafer surface was removed during dry oxidation. It may be noted that SiO2 film is growing on both the sides of silicon wafer. The next is the electrodes and heater patterning. Photolithography needs to be performed for electrodes patterning. The photolithography process includes the spin coating of photoresist, baking, alignment, and exposure, followed by developing of the pattern. The exposed photoresist will be removed from the selective area. Here the metal will be deposited for electrode over the patterned wafer. So after deposition, lift-off of undesirable photoresist need to be done in order to get the electrodes pattern. So students, let us now discuss sensing layer deposition. In order to fabricate Enose, different sensing layers needs to be deposited in order to detect multiple gases. Since we are taking the example of an array of 4 sensors, so 4 different sensing layers needs to be deposited. For each sensing layer, windows of photoresist are required to be opened, followed by sensing layer deposition. This process is followed 4 times for 4 different layers, and each time a different sensing layer is deposited. So the last process is cavity fabrication. Here the wafers were carried out for the photolithography for forming the cavity and bottom electrode. The photolithography process includes spin coating of photoresist, baking, alignment, and exposure, followed by developing of the pattern. The exposed photoresist will be removed from the selective area of the wafer, followed by etching of silicon dioxide using HF buffer or dry etching, and followed by etching of silicon using wet or dry etching. So this figure shows the different fabrication steps for Enose. Let us now discuss about the dicing and packaging. Since there are large number of Enose fabricated on silicon wafer, as shown in this figure, separation was performed using dicing, and they were get wire bonded to be used in electronic kit. So this figure shows a large number of sensors fabricated on a single wafer. Working and applications. All 4 sensors can be simultaneously exposed to given concentrations of the different gases. The response of each sensor for a particular gas can be plotted on a single graph, giving some pattern as shown in this figure. Radar plots or polar plots are convenient way to display multivariate dimensional data into the 2-dimensional data. The axis for each feature radiate from the origin at equal angles, and the magnitudes of the features joined by straight lines. A typical radar plot of the response data obtained from an array of 4 sensors is shown in this figure. Since each gas is behaving differently with these sensing layers, each gas will lead to some pattern. The pattern can be identified in order to identify the gas. Also, the amplitude or area under the curve for each pattern will help in identifying the concentration of the particular gas. So this figure shows the radar plot of the response data obtained from an array of 4 sensors. So students, let us summarize what we have learned in this module. First, what is Enose and MEMS devices were discussed. Second, we discussed the detailed sequential steps which are involved in the fabrication of Enose. Next, we were also discussed about the dicing and packaging. Lastly, working and applications were discussed in this module. Thank you.